This is SpaceTime, Series 19, Episode 84, for broadcast on the 25th of November, 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, massive water resources discovered on Mars. NASA's EM drive passes peer review, despite the fact that it apparently breaks the laws of physics. And a new crew arrives aboard the International Space Station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Frozen beneath a region of cracked and pitted plains on Mars lies about as much water as what's contained in Lake Superior, the largest of North America's Great Lakes. Scientists using NASA's Mars Reconnaissance orbiter spacecraft found the water ice deposits under the Utopia Planitia region of the red planet's mid-northern latitudes. An analysis of the data from more than 600 overhead passes using the orbiter's ground-penetrating shallow radar revealed a deposit covering an area more extensive than the Australian states of Victoria and Tasmania combined, and about the same size as the US state of New Mexico. The findings, reported in the journal Geophysical Research Letters, claims the deposit ranges in thickness from 80 to 170 metres in depth. Its composition is between 50 and 85% water ice mixed with dust and larger rocky particles. Now, at the latitude of this deposit, about halfway between the equator and the Martian North Pole, water ice can't persist on the red planet's surface, instead quickly sublimating into water vapour in the planet's thin, freeze-dried atmosphere. However, the Utopia deposit is shielded from direct contact with the Martian atmosphere by between 1 and 10 metres of topsoil. The study's lead author, Cassie Sturman from the University of Texas in Austin, says the deposit was probably formed by snow accumulating into an ice sheet mixed with dust during a period in Mars's history when the red planet's axis was far more tilted than what it is now. Today, the red planet has an axial tilt of about 25 degrees, similar in fact to the Earth's own axial tilt of around 23.5 degrees. And like Earth, large amounts of water ice have accumulated around the Martian poles. In cycles lasting about 120,000 years, the Martian axial tilt would have varied, reaching up to twice that 25-degree tilt it now has. That would have resulted in significant heating at the poles, driving ice towards mid-latitudes. Climate modelling and previous findings of buried mid-latitude ice indicate that frozen water does accumulate away from the poles during high tilt periods. The name Utopia Planitia translates loosely to the plains of paradise. The newly surveyed ice deposit spans latitudes from 39 to 49 degrees within the plains. It represents less than 1% of all known water ice deposits on Mars, but it more than doubles the volume of thick buried ice sheets known to exist in the northern plains. Ice deposits close to the surface on Mars are considered to be important. In fact, scientists think that this specific deposit is probably more accessible than most water ice deposits on Mars. That's because it's at a relatively low latitude and it lies in a flat, smooth area where landing a spacecraft would be relatively easy, especially compared to some other areas on Mars where there's known to be buried ice. Of course, the Utopian water is now all frozen. If there were a melted layer, which would have been significant for the possibility of life on Mars, it would have been evident in the radar scans. However, some melting can't be ruled out during different climatic conditions when the red planet's axis was more tilted. Utopia Planitia is a 330-kilometre wide impact basin dating to early in the red planet's history, possibly to the time of the late heavy bombardment between 3.9 and 4.2 billion years ago. NASA's Viking 2 lander touched down near the centre of Utopia in 1976, just northeast of the ice deposit location. Scientists focused on the region because of the intriguing ground surface patterns found there, such as polygonal cracking and rimless pits called scallop depressions. You see, similar landforms are found in the Canadian Arctic and they're always indicative of ground ice. However, scientists weren't sure if any of the ice would still be present at Utopia, or whether it would all have been lost over the billions of years since the formation of these polygons and depressions. It's important to expand on what science knows about the distribution and quantity of Martian water. We know early Mars had enough liquid water on its surface for rivers and lakes and even a northern hemispheric ocean to exist. What scientists want to know now is what happened to all that water. Much of it degassed from the planet from the top of the atmosphere. Other missions have been examining that process. But there's also a large amount of water in the form of underground ice, such as subsurface permafrost. One of the study's co-authors, Joe Levy, also from the University of Texas, says the ice deposits at Utopia Planitia aren't just an exploration resource. They're also one of the most accessible climate change records on Mars. Scientists don't fully understand why ice is built up in some areas of the Martian surface, but not in others. Sampling and using this ice in a future mission could help keep astronauts alive, while at the same time helping them unlock the secrets of the Martian ice ages. Scientists at NASA's Johnson Space Center Eagleworks Laboratories in Houston, Texas, have developed a new reactionless spacecraft propulsion system, which, if it really works, could take people to Mars in just 70 days rather than 7 months. But there's one really big problem with the system. It appears to violate one of the fundamental laws of physics. Newton's third law of motion, the conservation of momentum, states that every action has an equal and opposite reaction. It explains why a football's propelled when you kick it, and how a jet engine works to move an aircraft at speed. And that's the big problem. This new electromagnetic propulsion system, or EM drive as they're calling it, has no propellant going into the system other than the electricity needed to generate microwaves, and absolutely no exhaust coming out to propel the spacecraft in any direction. Yet, a report in the peer-reviewed Journal of Propulsion and Power claims it appears to work anyway. The trouble is the authors just aren't exactly sure how it works. The EM drive uses an asymmetrical cone-shaped copper chamber in which electromagnetic radiation, in this case microwave photons, are bounced around confined inside the cavity. As these photons collide with the chamber's walls, their momentum propels the device forward. No thrust is produced in the process, yet for reasons not fully understood, the EM drive appears to cause propulsion when operated. It's been suggested that the heat generated by the drive is heating up the surrounding air, causing a small amount of thrust. I guess that's a little bit similar to the Joukowsky effect we see in asteroids. However, the authors claim they're able to achieve exactly the same reaction when operating the EM drive on a torsion pendulum in a vacuum. British engineer Roger Scheuer, who first came up with the idea for the EM drive 2 decades ago, claims the system isn't really reactionless because the thrust comes from radiation pressure as microwaves inside the cavity create an imbalance of radiation pushing against the walls and generating thrust. The NASA team claim they've now achieved around 1.2 millinewtons per kilowatt of power in a vacuum, give or take 0.1 millinewtons. By the way, that kilowatt of electricity comes from solar panels. The authors think the thrust's being generated as the microwave photons inside the chamber push against quantum vacuum virtual plasma, the sea of quantum particles which constantly pop into and out of existence, giving us things like the Casimir effect. If successfully replicated by other groups, that would be very impressive, especially compared to other futuristic space propulsion systems, such as light sails, which are propelled by the push of photons coming from, say, the Sun, and which only generate between 3.33 and 6.67 micronewtons per kilowatt. Ion drives, which are far larger, can produce around 60 millinewtons per kilowatt, but they require fuel, usually xenon gas propellant, and of course solar radiation. In ion drives, gas in the form of neutral xenon atoms are injected into a magnetic discharge chamber where they collide with electrons. Electrons being negatively charged, the collision generates positively charged ions, which are then accelerated through electrodes to produce thrust and propel the spacecraft forward. For now, most scientists remain skeptical about EM drives. But of course that's going to change pretty quickly if others are able to independently replicate the results. We'll keep you informed. 3 new crew members have arrived at the International Space Station 2 days after blasting into orbit aboard a Soyuz FG rocket from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan.
First umbilical tower separating from the booster.
Auto sequence initiated.
We have auto sequence start.
Oxygen.
The engines igniting, the launch command issued. Again, the engines will fire, ramping up towards flight speed.
Engines at maximum.
And liftoff. Peggy Whitson, Oleg Novitsky, and Tomas Pesquet rocketing towards the International Space Station.
All 10 seconds, everything's nominal.
The rocket lighting up the night sky there in Baikonur. All initial performance calls indicate everything nominal or normal. First stage delivering 930,000 pounds of thrust through those 4 boosters in the single core engine. First stage measuring 68 feet in length and 24 feet in diameter. It's going to burn liquid fuel for the first 2 minutes and 6 seconds of the flight.
Copy.
Everything continuing to look steady, straight as an arrow for the Soyuz as it continues to rocket off. Again, launched right on time at 2:20 p.m. Central, 3:20 p.m. Eastern.
Everything's fine on board. Spherical tank pressure is nominal. We copy.
Over 70 seconds, 1 minute, 10 seconds into the flight velocity of the Soyuz, now over 1,100 miles per hour.
80 seconds into flight. Control and motion control systems are working nominally. Everything's fine on board. We copy. Thrusters of the second stage are working nominally.
All performance calls with the booster continuing to look great. Soyuz continuing to fly straight and true. The 4 strap-ons breaking away in the night sky there. The first stage boosters being jettisoned. Their job complete. They drop away at an altitude of about 28 statute miles. The Soyuz traveling at over 3,300 miles per hour. Now powered by the second stage.
Structure and the engines are nominal. Steering jettisoning. Confirm.
And so at this point, the launch shroud has been jettisoned. The Soyuz now exposed to the air and soon to space. The rocket at an altitude about 48 miles high. NASA astronaut Peggy Whitson making her 3rd journey to the International Space Station. At this point, the Soyuz traveling at a speed of about 4,700 miles an hour.
The crew is feeling fine.
So the second stage continuing to burn. That core stage that also flies during the first stage, performing as expected. That core stage, 56 feet in length, 13.5 feet in diameter, has a single engine with 4 fuel chambers and is providing between 178,000 and 222,000 pounds of thrust, depending on the altitude, for its 3 minutes and 28 seconds of operation. It will continue to burn until the 4-minute, 43-second mark, to when the Soyuz uses what's known as a hot stage technique, and that's the 3rd stage will ignite while the second's still burning. This is why the Soyuz has that small open grating area between the 2nd and the 3rd stages. The 2nd stage performing flawlessly so far. We are 4 minutes and 30 seconds since launch. Everything looking good so far.
We confirm 3rd stage engine activation. We copy.
Getting confirmation the 2nd stage has dropped away, separated at an altitude of about 105 miles. Soyuz now being propelled by the single engine of the 3rd stage, providing 67,000 pounds of thrust, going to burn for the next 4 minutes and 2 seconds.
Is nominal.
And again, this is the 3rd and final stage. It's going to continue burning until about 8 minutes and 45 seconds since liftoff, at which point the Soyuz will separate and be in its preliminary orbit.
340 seconds into flight. All motion control systems are nominal. Everything's fine on board. Copy. Roll, pitch, and yaw are all nominal. Everything's fine on board. And we hear you 5x5, and we see you on the video camera.
So over 7.5 minutes of flight. At this point, the Soyuz traveling at a velocity of almost 13,500 miles an hour. So there's just a little under a minute left in powered flight. Once the 3rd stage delivers the Soyuz to orbit and the module separated, those pre-programmed commands will be executed, preparing the Soyuz for orbital operations. All of these allowing the Soyuz systems to be automatically activated by onboard computers at precise times time stored inside. And some of those maneuvers will include deploying, again, those critical navigation antennas and the solar arrays that will power batteries, providing electricity to the various Soyuz system.
20 seconds till contact separation. Affirmative.
The third stage has cut off and separated.
Contact.
The confirmation coming from the folks in Mission Control Moscow. Third stage has separated successfully. That single liquid-fueled engine shutting down and dropping it away at an altitude of about 125 statute miles. And already getting confirmation from the visiting vehicle officer here in Houston. All of the different communication and navigation antennas have deployed along with those two solar arrays. So we have confirmation of spacecraft separation, deployment. The Soyuz now orbiting at an altitude of about 143 by 118 miles. That orbit's going to be raised systematically over the next 2 days as they chase down the International Space Station. Control of the spacecraft from here on out will be overseen by the Russian Mission Control Center just outside of Moscow. But for now, safely in orbit, NASA's Peggy Whitson, ESA's Thomas Pesquet, and Roscosmos's Oleg Novitsky, following a successful and a flawless launch in the early morning sky over Baikonur. So everything going very well with this Soyuz MS-03 vehicle so far. Vehicle in orbit, all of the antennas and the solar arrays deployed, and the chase down of the International Space Station has now begun.
While the new Soyuz MS series capsule used for the mission is now approved for fast-track for-orbit rendezvous flights to the space station, the Russian Federal Space Agency Roscosmos instead opted for a conventional 2-day rendezvous profile because Russia's new Klyon R command station in Voschesny, which is needed for fast rendezvous profiles for MS series Soyuz, is not yet fully operational. The Soyuz MS-03 capsule docked with the orbiting outpost's Earth-facing Razvet module, while both spacecraft were travelling at 28,000 kilometers per hour, some 400 kilometers above the ground. Its arrival brings the Expedition 50 crew on station back up to a full 6-person complement. The new crew face a busy 6 months in orbit, with at least 2 EVAs or extravehicular activities, that's NASA speak for spacewalks, as well as a full load of scientific experiments and numerous spacecraft arrivals also scheduled. In fact, the work began yesterday when an Orbital Sciences Cygnus cargo ship, which arrived several months ago, was undocked from the space station and moved out to a safe parking orbit. The manoeuvre was carried out because the capsule's to be involved in a dangerous experiment to see how flames react in a pressurized capsule in the microgravity environment of space. If it survives the experiment, the Cygnus, which is loaded with space station waste and refuse, will then be commanded to re-enter Earth's atmosphere, where it will burn up as it plunges to a fiery demise in the eastern South Pacific Ocean. In 2 weeks' time, a Russian Progress cargo ship loaded with 2.7 tons of fresh supplies will arrive on station. It'll be followed a few weeks later by a Japanese HTV supply ship carrying new lithium-ion batteries to replace the old nickel-hydrogen batteries on one set of the orbiting outpost solar arrays. The new batteries will be installed during a set of spacewalks slated for January next year. January should also see the arrival of a SpaceX Dragon cargo ship carrying more supplies for the orbiting outpost. However, this will depend on SpaceX returning to flight status following September's launch pad explosion, which destroyed a Falcon 9 and its telecommunications satellite payload. Another Progress cargo ship slated to arrive on the space station in early February, followed by a Cygnus supply ship at the end of the month and another SpaceX Dragon cargo ship in early March. Additional spacewalks are slated for March and April to attach one of the new international docking adapters to one of the Harmony module's pressurized mating adapters, thereby allowing it to be used to berth both Boeing's CST-100 Starliner and SpaceX's Dragon V2 capsules, both of which are slated to begin transporting crew to the space station in the next 2 years. Interestingly, the Expedition 50 mission means the International Space Station has now been continuously manned for more than 16 years and 3 months, making it humanity's longest ever continuous habitation in space. Two Chinese taikonauts have returned safely to Earth following a month-long stay aboard China's Tiangong 2 orbiting space laboratory. The pair landed aboard their Shenzhou 11 capsule on the frozen steppes of Inner Mongolia. During their 30-day stay in space, the crew conducted a range of experiments on long-duration human spaceflight. They also tested equipment needed for China's planned new space station, the first core module of which is slated to launch in 2018. The Tiangong 2 was launched into a 393-kilometre high orbit several weeks before the Shenzhou 11 crew blasted off. The Tiangong, or Heavenly Palace orbiting outposts, are considered stepping stones in Beijing's plans to establish a permanent space station in Earth orbit and eventually mining colonies on the Moon. China's original Tiangong 1 space station, which was used to test docking techniques, is still in orbit. But it's not communicating with ground stations anymore, and it's thought to have degraded its orbit thanks to atmospheric drag. Tiangong 1's now expected to re-enter Earth's atmosphere in an uncontrolled descent sometime next year, where it's hoped that it will burn up before hitting the ground. The United Launch Alliance have reconfigured their Atlas V 421 launch vehicle to handle Boeing's new CST-100 Starliner capsule, which is designed to eventually transport crews to the International Space Station. Together with SpaceX's Dragon V2, the CST-100 Starliner will finally give the United States its own way of accessing space following the premature mothballing of the Space Shuttle fleet in 2011. Starliners was slated to begin taking crew to the orbiting outpost next year, but that's now been put back until at least 2018. The reconfiguration of the Atlas V follows more than 6 months of wind tunnel testing. See, unlike other spacecraft carried by the Atlas V, the Starliner won't be launched inside an aerodynamic payload fairing. Instead, aerodynamic loads, which could damage the spacecraft, will be dissipated through a specially developed aeroskirt attached to the aft section of the Starliner service module. The aeroskirt's designed to deflect loads and increase stability during ascent to orbit. As well as the aeroskirt, the Atlas V 421 configuration also uses 2 AJ-60A solid-fueled rocket motors. The last time Atlas rockets were used to transport astronauts into space were in early versions of the ICBM during the Mercury missions of the 1960s. The Atlas V's also been selected by Sierra Nevada to carry its Dream Chaser manned spaceplane into orbit. The Dream Chaser is designed to be a crewed, vertical takeoff, horizontal landing, lifting body spaceplane. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.